Well, we've come to the last topic in Unit 2, and it's time to put it all together. I'm going to be discussing a model that we call the virtual source model. This is actually a very simple model now that does a remarkably good job of describing modern MOSFETs. And we're going to be revisiting this model as we go through the other units in the course, and we'll develop a deeper and deeper understanding of MOSFET physics through the use of this model. So what we have, if we go back a couple of lectures, is we developed a model for velocity-saturated MOSFETs that had two pieces. It had a linear piece for small drain-to-source voltages, and it had a saturated piece for large drain-to-source voltages. So we have this two-piece model, and what we would like is a smooth, continuous model that goes from linear to saturation. The transition region between these two is VD-sat. In this model, we make an abrupt transition from linear to saturated at VD-sat, but we would like to make that a smoother transition. Okay, so one thing I'll point out is that in the square law theory, the drain saturation voltage is VGS minus VT. In a velocity saturation model, there is also a drain saturation voltage, but it is always significantly less than VGS minus VT. The drain current saturates before the drain voltage hits that point. Okay, so the question is, can we take these models that we've developed and can we develop a smooth model that goes between the two limits? The way we're going to do that is with something that we call a virtual source model. The particular flavor that we're going to be discussing as the course evolves is due to a group at MIT, so I'll refer to it as the MIT virtual source model. We're going to be doing a very simple version of that model in this lecture. I'll call that a level 0 model, and it will get more and more sophisticated as we proceed. But you can see here the examples of the kinds of fits that you can get to experimental data in quite small transistors, and it works with comparable accuracy in even smaller transistors. All right, so this is our piecewise linear model. So we're assuming that the mobile charge above threshold is minus Cox, Vg minus Vt, that there is no mobile charge below threshold. We'll have to do better than that later because that mobile charge below threshold constitutes the leakage current that is important in modern transistors. We also have an expression for the current in the low drain to source voltage regime. And the way I'm writing it here is current is proportional to charge times velocity. In the low VDS range, the velocity is just mobility times electric field in the channel. In the high drain to source voltage regime, the velocity is just the saturated velocity due to the high electric field in the channel. That saturated velocity we call Vset. So if we could just make the velocity go smoothly from its low value over here, VDS minus VDS over L, to its high value Vsat, then we would have a smooth and continuous model. Well, there's an easy way to do that. Whichever velocity is smaller is the one that's going to dominate. And we can make that happen by saying 1 over the velocity is 1 over the linear region velocity plus 1 over the saturation region velocity. And whichever one of those is the smaller is the one that's going to dominate this expression. All right, you just put that expression together and put it under a common denominator, and we can do a little algebra and we get an expression that looks like this. We've collected up a few of the parameters, and those parameters we labeled VD-sat. It's just saturation velocity, channel length divided by mobility. Okay, so we can now then, with this expression, you can say we can write the average velocity as a function of the drain to source voltage times Vsat. And the function is just the business here, the business over here in square brackets. All right. That function we'll call Fsat. That's the velocity saturation function that takes us smoothly from the low drain to source voltage to the high drain to source voltage. And you can see that I've added a parameter. I've added a parameter called beta. It was 1 when we did this initially, and now I'm going to allow it to have some numerical value. Typically it's between maybe 1.4 to 1.8, and this is a value that helps us fit measured data. You can even argue as to why it should have a value of approximately this regime. But this is what makes our model semi-empirical. We insert this empirical parameter that helps us do a much better job of fitting data. And since it applies to a wide variety of MOSFETs, it's a very reasonable thing to do. So we have this semi-empirical saturation function, but the arguments I just given should hopefully help explain why it makes sense. We can take a look at that function. If we have a low drain to source voltage, we can ignore the VD over VD sat in the denominator, and that expression just goes to drain voltage over saturation drain voltage. We take that function times V sat, and that gives us the average velocity. We plug in the expression for VD sat, and we see what we have, and we just have mobility times electric field. Just what we know is the right answer in the linear regime. Okay, now in the high voltage regime, we can throw away the one downstairs, and you can see that FSAT times VSAT is just going to, FSAT is going to approach 1, so FSAT times VSAT is going to approach VSAT. That's the correct answer in the high voltage, high drain voltage saturation regime. So this expression does the correct thing in both limits, and it goes smoothly between the two. So although it's a semi-empirical expression, it provides good fits to a wide variety of MOSFETs, so it suggests that we're capturing something important that goes on in field effect transistors. Now, it's not the whole story, because we know that the current does not saturate in a short channel MOSFET. There's some finite output slope, which gives us some finite, non-infinite output resistance. So we also need to be sure that we treat that increase in current in the saturation regime with an increase in drain voltage. Well, we can see where that can come in. There's really not much we have to do to our expression. The current here is charge times saturation velocity. The saturation velocity is just a number, about 10 to the 7th centimeters per second for silicon. That's not going to change with drain voltage. The charge is minus Cox, Vg minus Vt. But we've seen that the threshold voltage does change with drain voltage. The threshold voltage is its value at low drain voltage minus a factor that is related to Dibble. So Dibble is a physical effect that lowers the threshold voltage as we increase the drain voltage. That lowering of the threshold voltage will give us more charge, it will give us more current, and that accounts for the finite slope in the saturation regime, which is really not exactly a saturation regime, but in a well-designed transistor, the slope here will not be too large. Now, I'll point out also that we sometimes talk about channel resistance. The channel resistance, we would go in the linear regime. We would fit a straight line to that expression. We would take our linear region current expression, and we would write it as drain to source voltage divided by channel resistance, and that would give us an expression for the resistance of the channel in its linear regime. Sometimes people call this the on resistance if we're doing this at the maximum gate voltage. Okay, now that's not the whole story. If we were to measure the resistance between the source and the drain in the linear regime of a MOSFET, we would find that we typically get more than the channel resistance. And that's because any real MOSFET has parasitic resistors. When we make a metal contact to the drain, make a metal contact to the source, even when we make a metal contact to the gate, we're going to have some resistance between that contact and the silicon itself. So that introduces series resistances in the drain and the source. I'm not showing one in the gate because there should be no DC gate voltage, so there's no volt drop across any resistor that might be there. All right. Now that resistor can be important for things like RF applications, but for our DC analysis, we don't need to consider it. So how do we include the effect of these parasitic resistances, which are always there and are important in our model? Well, it's relatively easy to do. What we have is a model for the intrinsic device, a device without these extra resistances. I'm going to label those intrinsic voltages as VGS prime and VDS prime. So the IV characteristics that we've talked about earlier really refer to the VGS prime and IDS prime. The actual voltages that we apply to the drain and the source and the gate and the source have to account for the extra volt drops across these series resistors. That's easy to do. There's nothing to worry about in the gate. In the drain, the voltage between the voltage at the drain is the voltage at the intrinsic drain is the voltage we apply to the drain contact minus the voltage drop in the drain series resistance. And the voltage at the source is actually positive, even if we ground the source terminal, because there's a voltage drop as the drain current flows through that series resistance in the source. So we can simply map the intrinsic characteristics to the extrinsic characteristics in this way. Now, what is the effect on IV characteristics? Well, if this is an intrinsic MOSFET, some ideal MOSFET with no series resistors, if we actually have series resistors, we'll measure something like this. Down in the linear regime, we're not just going to have the channel resistance, we will have the channel resistance plus the source series resistance and the drain series resistance. Now, up in a saturated regime, we also have less current. And that occurs because the voltage between the gate and the source of the intrinsic device is now less. Because the series resistance in the source leg means that there's a volt drop across that resistor, means the intrinsic source is really at a positive voltage. So the voltage between the gate and the source of the intrinsic device is less than it was without the presence of that resistor. So series resistances are bad. When we develop technologies, we try to keep them as small as possible to try to minimize these detrimental influences. All right, so we can summarize very simply. We've developed what I'll call a level 0 virtual source model, and we'll make it more and more sophisticated as the course goes along. Current is proportional to charge times velocity. The charge, for right now, we're taking a very simple expression for the charge. We'll see how to make this more sophisticated and account for the charge that's there below threshold as well. We'll see that in the next unit. The average velocity is this function fsat times the saturation velocity. And that function is semi-empirical. It's based on some physical reasoning, but it includes an empirical parameter, and it smoothly connects the velocity in the linear regime to the velocity in the saturation regime. And there is a transition between the two that occurs smoothly around the voltage we call VD sat, which is significantly less than VG minus VT in the square law device. Okay, now there are only 8 parameters in this model. That's what makes it relatively nice. And most of these models are quite physical. We know what they refer to. It's not simply empirical curve fitting. Each one represents something very physical in the MOSFET. There is one empirical parameter that we've introduced, but that doesn't change much from transistor to transistor, and it helps us fit the data better. So what is the physics of this model that we've introduced? Well, it's based on what we would call diffusive or collision-dominated transport. When there are lots of collisions, concepts like mobility make a lot of sense. It's a little less clear if they make sense in the ballistic regime when there is no scattering. We've assumed that when the field is high, that there is so much scattering that the velocity is clamped at the high field saturation velocity, 1 times 10 to the 7th in silicon. Now, the difficulty is neither of these assumptions is valid in modern transistors. Now, we can see that these are some sophisticated numerical simulations of electrons moving across from the source, across the channel, and out the drain. In this particular case, this is a simulated 30 nanometer channel length transistor. When these simulations were done several years ago, this was almost an unimaginably small channel length. Today's state-of-the-art technology has channel lengths that are even smaller. You can see each dot represents an electron streaming across from the source to the drain. If we plot the average velocity of all of those electrons versus position as we go from the source to the drain, you'll get a characteristic that looks like this. And if you look at that, you'll say, wait a minute, my high field saturation velocity, presumably the fastest electrons can go in silicon, is 1 times 10 to the 7th right there. But you can see that over the entire channel, the electrons are going significantly faster. Now, to treat this quantitatively involves a lot of detailed considerations of band structure and scattering physics. But the basic reason that this is occurring is because the electrons are zipping across the channel so fast that they don't have a chance to scatter very often. They get out of the device before the scattering has been able to slow its velocity down to 1 times 10 to the 7th. So this phenomenon is called velocity overshoot, and we know that it's present in modern transistors. So that brings us to the importance of transport in MOS transistors. We can think of transport in one regime where electrons just enter the device from the source and zip across without scattering like they might do in a vacuum tube. Nothing impedes their motion. We would call that ballistic transport. And we are getting to the point where that can be observed in some modern transistors right now. In more realistic transistors, and especially in older transistors with longer channel lengths, the electrons encounter impurities and lattice vibrations and various things that can knock them in random directions. We call that scattering. So that is diffusive transport if there is a lot of scattering. Modern transistors, we would say, are in the quasi-ballistic regime. There is enough scattering that we can't consider the transport ballistic. There's not enough scattering that we're fully diffusive and that we can use concepts like mobility and saturation velocity and feel comfortable with it. But these are some of the issues that we're going to be discussing and developing an understanding of when we get to Unit 4 of this course. Okay, but I just want to point out that this particular model, in spite of these concerns about the physics upon which it is based, does a remarkably good job of fitting the IV characteristics of modern transistors. This is an example that I showed you earlier of the kinds of fits that you can easily get to very short channel transistors. So there's something in this model that is right, that is capturing some essential physics, and we have to understand what that is, how the model can perform so well, even though it's based on this shaky physics. And what we'll see is that if we simply replace the mobility by something we call an apparent mobility, and if we replace the saturation velocity by something we call an injection velocity, now we will show that these are more than two curve-fitting parameters, that these are really parameters that have physical significance. And part of our goal, especially when we reach Unit 4, will be to explain the physical significance of these parameters and why they work so well in describing the characteristics of modern nanoscale transistors. Now, as we proceed in the course, we're going to focus a lot on what we call the virtual source. So you'll remember how we described the operation of transistors in terms of energy band diagrams. Current flows because we manipulate the potential energy barriers. When the device is off, there's a high barrier. We only have leakage current. When we apply a high gate voltage, we pull the barrier down. Electrons can flow out of the source, into the channel, across it, and out the drain, and current flows. At the top of the barrier, this is going to be a particularly important point to us. When we focus on the top of the barrier, we're going to call that point the virtual source. And we will see that at that point in a well-designed transistor, there's a very simple expression for the charge. It's the classic expression that we have been using in a long channel transistor. If that expression is valid, it makes the analysis of these very short channel transistors much easier, and that's the reason that we are going to focus on this point we call the virtual source. Now, I'll point out that as we increase the drain bias and sweep it from small to large, in a well-designed transistor, this is nearly independent of the drain voltage. There'll be a small amount of dibble, but hopefully a manageable amount. And all of this is only true if we have designed the transistor carefully and appropriately from an electrostatic perspective. That's really the major job of the transistor designer, is to design the electrostatics such that the charge at the virtual source is a simple, nearly constant value that is given by this expression. Okay, so our virtual source model focuses on the charge and the velocity at the virtual source. And this is the model that we've summarized, which takes our two-piece model and makes it into a continuous connection of linear to saturation region currents. Now, I'll point out that one of the attractive features about this model is that it has only a few parameters, and those few parameters have a very sound physical basis. They're easy to understand what a series resistance is, what a mobility is, what a saturation velocity is. We're going to have to develop a deeper understanding of what these parameters mean in nanoscale devices, but they have physical meaning in nanoscale devices as well. And then there's one empirical parameter that we add, which doesn't change much from transistor to transistor and really helps us fit devices very accurately. So, we've come to the end of Unit 2. In the next lecture, I'm just going to recap the main points that we've covered in Unit 2, and that will get us ready to proceed on into Unit 3.